Cool. Hi, everyone. My name is Francesco. I'm an Imperial College Research Fellow. I'm based in South Kensington, Department of Computing. My research has me look into problems related to explainability, but not just that. There is a bit of explainability. There is a bit of robustness. So I guess different topics around, within the trustworthy AI area. Now, today with this talk, I would like to, well, as you see from the title, this is something that kind of puts different topics together. The reason why I decided to talk about robustness issues in algorithmic recourse is because it also has some interesting connections to fairness, which I thought would be appropriate for this seminar. Fine. Okay, in case you don't know what algorithmic recourse is, don't worry, there is a slide on this, and I would like to start from there. So what does algorithmic recourse mean? Well, actually, algorithmic recourse is the problem of indeed providing recourse recommendations to users that have been negatively affected by the decisions of a machine learning model. In my case, it's a deep neural network. Generally speaking, it could be whatever, a machine learning, an AI model, whatever that means. Now, here, for instance, I'm showing this often used and abused example of a loan application scenario where a person applies for a loan. We are assuming here that the loan application can be characterized in terms of three features: the age of the person, the amount of the loan, and the duration of the loan. And now suppose there is a financial institution somewhere that is using a deep neural network to decide whether the loan should be granted or not. And unfortunately for this person, in this case, the computer says no, so the loan is denied. Okay. Now, what is the problem of recourse in this case? Well, basically, we want to give suggestions to this person as to what needs to be changed in their application, such that next time they apply, the application will go through and the loan will be granted. Okay. Now, there are different ways to provide recourse recommendations. In my work, I use counterfactual explanations, which is kind of one of the mainstream approaches for providing recourse recommendations. What is a counterfactual explanation? I'm showing an example here. Bear in mind, this is a fictional example, so don't try to understand whether the number makes sense or not. But a counterfactual explanation in the context of deep learning in particular is typically defined as a minimal set of changes to that need to be applied to the input, such that the machine learning classifier that is deciding will produce a different and typically desirable classification outcome, okay? So in this case, as you'll see, if we reduce the loan amount from 15K to 10K, the loan will be approved. And the counterfactual explanation, as an example here, the counterfactual explanation will read like this. So the application would have been accepted had you asked for less, okay? Yes?
Could this recommend that if you were 50 years old, you'd also be?
Yeah, so, okay, this is a property that is known as actionability or feasibility. If you're not careful, yes, that can happen. But in principle, this is one of the properties we care about when generating counterfactuals. We only want to provide recourse recommendations that are feasible, actionable, and reasonable ultimately. So, but yeah, it could happen. So yeah, this is what a counterfactual explanation is. Now, for the sake of this presentation, I will distinguish between two different types of counterfactual explanations. But before I do that, I need to introduce the concept of a counterfactual distance. Now, what is counterfactual distance? Basically, here we're given the instance X, which is the instance for which we're trying to compute the counterfactual explanation. We assume the availability of a distance function. This is a distance function over the input space. This is the space where X belongs to. And we have a classifier. As I said, could be a neural network or anything else. And now the counterfactual distance is the infimum of that set. So you basically take all the points in the input space, which produce a classification that is different from the one obtained for C. Okay, so this is what this means. And then you take the distance from X and Y, and you take the smallest one. So this is the counterfactual distance. Okay, so based on this notion, we have two types of counterfactuals. The first one, for a point X prime, we say that X prime is a strong counterfactual if it is the nearest one, okay? If the distance between x and x prime is the smallest possible. So that in that case, we call x prime a strong counterfactual. Otherwise, we call it epsilon approximate. So it basically means that it is close enough, but an epsilon away from the minimum distance, okay? Whatever epsilon you might want to choose. Fine. Now, how do we compute these counterfactuals? Let's start from the strong counterfactual. I guess the most sort of the most commonly used, but also the most basic formulation that can be used to compute a counterfactual explanation is this optimization problem here, which basically says, given the instance, the classifier, and a distance function, so this guy here, which tries to find an x prime, the counterfactual, which minimizes the distance between the counterfactual and the original instance, subject to the constraint that the classification needs to flip. Okay, and this basically means give me another instance for which the loan is accepted. The classification changes. Okay. This is the most, as I said, the most basic one, because obviously one could think of additional constraints to be added here, such as actionability. That is one of the most sort of commonly used constraints. Now, this problem can be solved exactly if you have a model. Let's put it this way. The problem can be solved exactly for some classes of machine learning models. For instance, if you have a deep learning network with piecewise linear functions, activation functions, then we know that this problem can be solved exactly. You encode everything into a mixed integer linear program that obviously also depends on your choice of D. But there are some instantiations for which the problem can be solved exactly. What if it cannot be solved exactly? Then we move to the next formulation, which is proposed in the paper, which was originally proposed in the paper down there. And this is, I must say, probably the most commonly used formulation in the literature, especially within deep learning. Basically, it's again an optimization formulation where you try to find a point x prime, which is your counterfactual. But now the point x prime is kind of, the choice of x prime is kind of driven by two different objectives, or loss terms. The first one is L. Now, L is a differentiable loss function, and what it does, it minimizes the gap between the prediction that the classifier gives for x, the original point, and the prediction for the candidate x prime that you are evaluating at that particular step, okay? So L effectively drives the search towards points that obtain, that sort of yield the desired classification. That is the role of L. The second bit is this lambda times D. D is still the distance as defined, as used in the previous slide. And now lambda is just sort of a knob that we have that we can use to tune the importance of the two loss terms, right? So whether I want to sort of give more importance to the distance or the first term, lambda is kind of the knob I have, the knob I can use, okay? So these are the most, as I said, the most basic and the most commonly used formulations. Now, let's start with sort of the robustness issues that were also mentioned in the title. Now, I guess the question now, and also the title of this slide, is as you can see, are we sure that minimizing distance alone is a good idea? As you can probably understand, the answer is no, because I've just started. So otherwise, but why is it not a good idea? Well, there are many reasons. One of them was discussed in this paper here by some colleagues at Harvard, who basically showed that if you generate counterfactual explanation by, or rather, let's put it this way: if the only thing you care about when generating a counterfactual explanation is minimizing distance, you might end up returning explanations which are indistinguishable from adversarial examples. Now, what is an adversarial example? In case not everybody's aware, basically an adversarial example is a point in the input space where the neural network doesn't know what to say, right? And it's kind of like a blind spot for the neural network. The neural network will just say some rubbish. It doesn't really know. You shouldn't really trust what the network says on an adversarial example, right? And now, hopefully you can understand why returning an adversarial example or more precisely, returning a point, a counterfactual that is indistinguishable from an adversarial example, and using that point to explain something doesn't really make sense, because basically you're taking a point where the network doesn't know what to say, then you're giving it to the user, and you're asking the user to trust that specific explanation that you're giving, but the model itself doesn't know what to say in that point. So, it becomes a bit tricky here. On top of that, there is an additional element that when you minimize distance, basically what you're trying to do is you're trying to return points that lie exactly on the decision boundary. Especially if you return a strong counterfactual, you will be exactly on the decision boundary. And this is what I'm representing here. This is a figure from this paper, where basically we see two classes. This is what, blue and red. And these are the original instances for which you want to compute a counterfactual. And these are the counterfactuals. But you also see for instance, here in this on the right hand side, the red circles are adversarial examples. The green ones are the explanations. You see they coincide and they both lie at the decision boundary. Why is this a problem? Well, in a nutshell, it is a problem because as soon as you change something, as soon as you change something in the setting for which the counterfactuals were generated, the decision boundary will likely move a bit, or these points will likely move a bit, and the validity of the counterfactual will be affected. And this is kind of summarized here. If I can rephrase a bit, when you use nearest counterfactual explanations to provide recourse recommendations, you need to pay attention, because if anything changes in the problem you're considering, the recourse recommendation that you're offering may cease to be valid. Okay, which basically means if we go back to the loan application, I could find situations where I'm giving recommendations to the user, earn more, get a degree, you name it. And then something changes, either because you have new data coming in and you update your model a bit, or maybe because other reasons, the recourse recommendations might be invalid. And then at the end of the day, you get a user who got a PhD because you told them to get a PhD because it's good for the loan, and then they go back there, and turns out the PhD wasn't enough. Now, on a serious note, there are several possible threat models, so things that might invalidate the recourse recommendations. Input changes, model changes. For this talk, I've decided to focus on the first one, input changes, because I think that's the one that has interesting connections with fairness. But I've also done work on the other threat models, so if you're interested, I'm happy to discuss this later. Now, what do I mean by input changes? So I put this example here. Basically, what we see here is, again, sort of a fictional representation of the input space. Two classes. Whatever goes inside the circle is rejected, if we're still talking about the loan application, and whatever is outside is accepted, okay? Green and red, this is what they mean. Now, we start from the original instance that was rejected, we know, right? And for this original instance, we try to compute a nearest counterfactual explanation, or a strong counterfactual, right? And this is what we might obtain, okay? So basically, as you see, you try to find the nearest point that belongs to the other class, which basically means the nearest point that flips the classification. And this is what you get. So these are the recourse recommendations that you will be giving to the user. Now, suppose a new user comes in, okay? So this white cross. Now, this user is very similar to the first one, right? As you can see, the only difference in this example is that they're asking for a bit more, so 1K more. But other than that, they are very similar. Now, what happens when you compute a strong or a nearest counterfactual explanation for that new user? You return a completely different counterfactual explanation, whereby completely different, in this case at least, I mean very far away from the other counterfactual explanation that was generated for the first user. Why is this a problem? Well, the problem is that now we have two similar users. They're getting two very different recommendations, okay? So this, hopefully I've managed to convince you that this is problematic, but I'm not the only one who thinks that this is a problem. Now, for instance, we have this interesting paper here, Robustness in Machine Learning Explanations. This is a paper that came out, in fact, 4 years ago now. And basically, the point that is discussed in that paper is that humans have this expectation here that similar phenomena get similar explanations. Or in other words, in our case, similar individuals should get similar explanations. What happens when this doesn't hold anymore? Well, users receiving counterfactual explanations might start wondering, are we sure the explanation was actually explaining anything, or was it just, an artifact of the model? Should I trust this explanation? Is it really telling me anything useful? That is mostly because, again, kind of reinforcing this point, we would expect that neighboring inputs, we would expect they're processed in similar ways by the machine learning model, right? And when this doesn't happen, you start questioning the ability of the machine learning model to, or rather the validity, or you start wondering whether the machine learning model is useful at all. So we definitely do not want to have such variability in when generating counterfactual explanations. Even worse, in 2021, this paper came out, Counterfactual Explanations Can Be Manipulated. And this is a paper where the authors showed that neural networks, in particular for this paper, deep neural networks can actually be trained maliciously to actually, aggravate this behavior, to exaggerate, to basically show this complete lack of robustness. But it's actually even worse than a natural lack of robustness, because in this case, it's actually adversarial, which basically means, at least in the context of that paper, that the authors had ways to to train neural networks that would discriminate, that were unfair. These networks were unfair, but they were not unfair at the level of inference, right? So in the most common case, you would expect that the machine learning model is fair across different groups at inference, right? In this case, the models were unfair at the sort of meta level of recourse generation. So they would generate more favorable recourse to individuals belonging to particular groups. I believe in the paper they have, I think the key sort of factor is gender, and basically they showed that following their procedure, neural networks could be trained such that standard counterfactual explainers that only care about minimizing distance would produce better recourse recommendations for men, I think, than women. I think this was the example they had in the paper. But this is yet another reason why while robustness is important and a lack of robustness is problematic. But what is why do we observe this lack of robustness? So this is the question that we investigated with a colleague of mine, Nico Potica from the University of Cardiff, and it's something that we discussed in a recent paper of ours that appeared at AAAI earlier this year. Basically, we looked at this problem of robustness to input changes, and the first question that we asked was, why is it that these counterfactual explanations are not robust? Well, the observation is, in a way, very, very simple. Basically, as long as there exists more than one potential counterfactual explanation for a given instance, if you return a single counterfactual, and moreover, or even worse, if you return a single nearest counterfactual, then you're bound to lack robustness. And the proof is, sort of the intuition is kind of trivial almost, because you're here, you return this guy here, you move an epsilon away from this black cross, and you immediately end up returning the other point, right? So the first key takeaway message is that if you want to be robust, maybe you should stop returning single nearest counterfactual explanation. Mm-hmm. Fine. So that is actually the second idea that we put forward in the paper, where we said, okay, fine. If single nearest counterfactuals are not good, then let us return sets of counterfactual explanations. And this is what I mean here in this example, in this, in this vignette. You see, for the same instance, I'm returning a bunch of them, in fact, effectively, a number of counterfactual explanations. Why is this useful? Well, look at this example now. What happens when, for the first, I have a set for the first instance, then I move an epsilon away from it, and now I compute another set for the second instance. Basically, what we showed in the paper is that in some specific, under some assumptions, let's say, returning sets of counterfactuals guarantees some degree of overlap between the two sets. Okay, what does this mean in practice? Well, what it means in practice is that the first user will get some recommendations or some recourse recommendations that will also be given to the other user. Okay, so in this sense, as the title, as the title of the paper suggests, we are promoting the robustness. Now, diversity will come in a bit later, and I'll show how. But yeah, so this is kind of the intuition behind the paper. Now, how do we do this? How did we do it? Well, the first step for us to understand how we achieve these results requires the introduction of this notion of distance between two sets. Okay, many different possibilities. Here, for instance, if we consider an explainer, an algorithm that returns a set of counterfactuals for an instance, so the instance X, a classifier CL, the explainer returns a set. Now, the intuition that we would like to capture is that when we have 2 points, X1 and X2, we would like that some of the, well, ideally, for each counterfactual in the first set, so the set computed for X1, there is also a closed counterfactual in the other set X2, right? Which is exactly the situation that we had here. So for each counterfactual in the first set, we have a closed one in the second set. Now, what does it mean to be closed in this setting? This is the proposal we came up with. Now, this I had to put an equation here, so, but it's just one of the several possibilities that we discussed in the paper. What this means is just an average of the maximum distances between points in the two sets, right? So you have two sets, you start from the first set, you pick a point, compute all the distances, you take the maximum, you repeat for all the points in the set, you do the same starting from the other way around, and then you average the maximum distances here, okay? So effectively, this kind of gives you the largest distance within the two sets. We also have other options discussed in the paper, but yeah, this is just to give you an idea of what a distance might look like in this set. Okay, so now that we have a notion of distance, we can start formalizing the robustness property, and we can start discussing effectively some of the properties that we would like to enforce on these counterfactuals. The first property that we formalize is this epsilon k robustness. What does it mean? So we have, as usual, we have the explainer, we have a pair of inputs, such that the classification for these two inputs is the same, okay? And the distance between these two inputs is bounded by epsilon, so the two inputs are close enough. So these 2 points are effectively similar, okay? We say that the explainer is epsilon k robust if the distance between the sets of counterfactuals is proportional to the distance between the 2 points, okay? So this is what this means. So we have the two sets, and we want that the distance between these two sets is bounded above by, well, k times the distance between the two inputs. Now, although this this is kind of it would be a very nice property to have. However, in the paper, we showed that satisfying this kind of robustness may be impossible in general. And this is the counterexample, basically. So what you see here is that if you take this point and you compute a nearest counterfactual here, then you and you do the same for this other point here, what happens now is that basically these 2 points, you can bring them as close as you want. You imagine moving the 2 crosses towards the sort of the center of the circle. So we'll have that the distance between these 2 points kind of tends to 0 in a way, but the distance between the counterfactuals doesn't change. Okay, so this is why, in general, guaranteeing epsilon k robustness might be impossible. So basically, this kind of forced us to come up with a weaker notion of robustness, which is weak epsilon robustness. And now, same setting here. Again, 2 points classified the same way. The distance is bounded. And we say that now the explainer is weakly epsilon robust if this statement is true. Basically, if we have a point in the first set of counterfactuals, so x1 prime, okay, and x1 prime is a strong counterfactual for x1, then we require that x1 prime is also contained in the other set. Now, the interesting bit is that it doesn't, we're not asking that x1 prime is strong counterfactual for x2. So we are happy if x1 prime is an epsilon approximate counterfactual. And again, this mimics that situation where some of the options that were given to the first user will also be given to the second user. Now, there is one interesting point to discuss here. There is, we can only retain strong counterfactuals. If the first set contains epsilon approximate counterfactuals, we cannot guarantee that these points will also appear in the other set, okay? So basically, as soon as you start moving away from the original instance, some epsilon approximate counterfactuals might be lost, okay? Now, this is the property that we want to guarantee, but can we actually build an explainer that satisfies this property? Well, the first answer is that yes, in theory, this is possible. How do we do it? Well, we do it using this exhaustive epsilon approximate explainer. What is it? This is, again, an abstract object that returns all the epsilon approximate counterfactuals for a given instance. So you imagine, if you go back to the sort of the vignette we had earlier, you have a point within the red circle. The epsilon approximate explainer will, the exhaustive epsilon approximate explainer will return all the counterfactuals, all the epsilon approximate counterfactuals for that instance. If we had a counterfactual explainer like that, we could guarantee this kind of robustness. So basically, if you use the exhaustive epsilon approximate explainer, as long as you move within an epsilon, well, actually half epsilon radius from the original point, you can guarantee the satisfaction of this weak epsilon robustness. Obviously, the problem here is that in practice, this exhaustive epsilon approximate explainer doesn't exist, or it's not possible to realize it. Why? Because the number of epsilon approximate counterfactuals may be infinite for a given instance, right? Because we're talking about, imagine if we're talking about real numbers, if your features are reals, then the number of epsilon approximate counterfactuals may be infinite. And then obviously this kind of defeats the purpose, because at the end of the day, we should not forget that we're trying to provide recourse recommendations to users. As much as we like theoretical, or I like theoretical sort of problems, then what's the point if you cannot use it in practice? Well, for this reason, in the paper we propose an approximation scheme. So you have this object, the exhaustive explainer. It doesn't exist in practice. We approximate. How do we approximate? We do it using diversity, and that's why diversity also appears in the title of the paper. Basically, here, instead of showing the pseudocode for the approximation scheme, I decided to put this. Hopefully, this will be more intuitive. The approximation scheme is based on a very simple counterfactual explainer which is the nearest neighbor counterfactual explainer. The nearest neighbor counterfactual explainer is, as the name suggests, an algorithm that is based on nearest neighbor reasoning. So what does it mean? It means that if you take this example here, suppose this is the instance for which you want to compute the counterfactual. You look at the points in the data set that are close enough, but that belong to the opposite class. Again, here we are in the binary classification setting. So you start from the orange circle. You return the nearest neighbor that belong to the opposite class. Okay, so these are points 1 to 5. That is our starting point. Now, these points, after we have identified the nearest neighbors, we sort them according to distance. And the first thing we do is we drop those points that are too far, okay? Because let's not forget that the exhaustive explainer is only returning epsilon approximate counterfactuals. So we have this notion that you shouldn't be too far, basically. So that is why, for instance, number 5 disappears. Now we have this set of counterfactuals, which give us a sort of a good characterization of the decision boundary, right? Because with all these points, now we kind of know where the decision boundary is here. However, as I said earlier, the number of counterfactuals here can be very large, right? So one thing we can do to reduce the number of counterfactuals is to drop those counterfactuals that are too similar, okay? Because there's no point in returning, hundreds of counterfactuals if they're all giving you, basically, if they're all telling you the same thing, right? If you want to return counterfactuals that are informative. And that's where diversity comes in. Diversity is a common criterion that is sort of used in the counterfactual literature, and it really means what it means, right? So you want to have points that are different. And so using commonly studied diversity metrics, we basically filter those counterfactuals that are too similar, okay? So basically what we're left with is shown here. So we have a set of points. These are our candidate counterfactuals. If you really care about minimizing the distance, you can do it. So once you have these points, you do some line search or whatever you want to do, and you bring the point closer to the original instance. Otherwise, you can stop here and return these points as counterfactual explanations. So yeah, this is, in a nutshell, this is what we did. Right, yeah, just one slide on experiments, just to show you that we did our homeworks, and that it works. So basically what we did is we compared our approximation scheme with DICE. Now, DICE is an algorithm, a gradient-based algorithm that has been proposed to generate sets of diverse counterfactuals. Bear in mind that DICE wasn't conceived with a robustness property in mind, right? So the only thing it does is it returns a set of counterfactuals, diverse counterfactuals. So basically, what we wanted to see was that basically we used DICE as a baseline, and we wanted to see whether our approximation scheme was actually useful or helpful in improving the robustness of these explanations. So we took 5 data sets. These are all tabular data sets for binary classification problems. And what we did is basically we followed this protocol here. So you start from an instance, x1, generate a set of counterfactuals for x1, then you perturb x1 to obtain a similar instance x2, repeat, so compute a set of counterfactuals for x2, and then measure the distance between these sets, right? So ideally, if your algorithm is robust to input, if your explainer is robust to input changes, then the distance will not increase much. The distance will be small. We repeated this a number of times to ensure sort of statistical significance. And then, of course, we also looked at other properties that are commonly studied in the literature. Validity, which is the ability of a counterfactual to effectively flip the classification. The distance from the original input and the set of counterfactuals, and other properties, okay? And basically, here, the key takeaway is actually this line here. This is, again, just for, because I wanted to show off, and I wanted to, I do have numbers in my paper. No, but actually, what we can see here is that the robustness is improved. As in, if you follow this simple procedure, you can actually observe improved robustness. And as a byproduct, which was actually quite interesting, we also obtain better diversity within the sets, and we have a considerable improvement in the runtime. So basically, we outperformed the DICE baseline along different dimensions. Why is this interesting? Well, results aside, why is this property interesting, and why is this scheme interesting? Because there's a lot of work in the deep learning, in the machine learning literature in general on fairness, as you might know, and there's a lot of work on recourse fairness. Okay, obviously you want to compute recourse recommendations that are actionable, valid, but you also want them to be fair. And there are some very interesting connections between the properties that we've studied in this paper and the some of the most commonly used notions of fairness in the recourse literature, right? So basically, in a way, as a next step for this work is to study these connections and to basically establish whether being robust is also helpful in the sense of fairness. And I think the answer is yes, although we don't have a theorem yet. But there are these interesting connections between the robust literature and the fairness literature, which I find very exciting. Now, that's it. If you have questions, this is a good time to ask. But if you're interested in the other notions of robustness that I've discussed, you can scan that or just visit my webpage. Because there's a lot more. I mean, I've done work on robustness of counterfactual counterfactual explanations when the underlying machine learning model is retrained. So what happens when you have your model, you compute a counterfactual, and then suppose new data comes in, you fine-tune the model because you want to incorporate this additional information in the model. But then this fine-tuning step might actually invalidate the counterfactuals that were generated initially. There is model multiplicity. This is another interesting topic within the deep learning literature, not just deep learning, in fact, where basically model multiplicity refers to a scenario where you use the same data to train machine learning models, but then you change something, could be the seed that you use for training or other things, and you end up having several models that have high accuracy. So they're all good models, but they differ in their internals. And this difference will show when computing recourse recommendations. Anyway, there's a lot more. Happy to answer your questions now if you have any. Yeah, that's it.
What is the set distance? How is that your results, let's say L2 column? The set distance, the sigma.
Yeah.
Then, for example, the diabetes case, that's 4.10 plus minus 0.11. Diabetes hours L2.
Left.
Yeah, there.
Right.
So what does it mean, like in practice? How should I now read? It's like compatible within one standard deviation to be 0. So what does it mean in practice?
For that specific number, or are you asking about the metric?
Well, both. That number and then the metric. And what does it mean in practice? So 3 questions.
Okay, so what does it mean in practice is that there is some degree of overlap between the points. The points are not the same. Yeah, we're not returning the same points for both X1 and X2, right, in this protocol that we used.
Right.
But
between 1 sigma, they are the same.
They are close enough. They are close enough, okay? Now, then, if you want to be even more concrete, so in a specific application, this could mean that one person is recommended, say, to increase their salary or say reduce their loan amount by 5K, and the other one would be told to decrease by 4.5 in a very specific application. Now, the variability. So here it's as you said. So sometimes you know they're closer than in some cases they're closer than in other cases. Right, and you had a third question.
Well, I mean, if I just compare with all the other, you have this K diversity, K distance there, like the K diversity, for example, is like 0.78 plus minus 0.50. And that's like several standard deviations from 0.
Right.
So it's like 3 sigmas or something.
Yeah, fair. So there is, I guess part of that is has to do with the way these metrics are defined. So these are, for instance, these are metrics that we took from the literature, and although they are normalized, I think they use slightly different normalizations, which might explain the higher values. But there is less variability, and I think the variability in our case, in particular, has to be or can be attributed, or it can be explained in part at least by the specific approximation scheme that we used, right? Bear in mind that these results they're only telling you something about how good our approximation scheme is. But the first part where we had this the sort of the theoretical analysis that will hold irrespective of this, right? I guess one takeaway from this, or one way to answer your question, is that the approximation scheme can be improved to ensure that there is less variability within the sets. And there are many ways this approximation scheme can be improved. As I said, we rely on this nearest neighbor explainer to begin with. Other things are possible. So I'm assuming this is just speculating now, but I'm assuming that using a prototype. I don't know if you're familiar with prototypes. This is another type of explanations.
Probably not in this context, no.
But you can think of it as some sort of clustering, where you try to find the, for a given class, you try to find the most representative prototype of that class. So I'm assuming that using prototypes to begin with might result in less variability. But yeah, that is one possibility. Also, the diversity criteria that we used in the paper, there's like a lot of different criteria that could be used. We only used a distance-based or angle, like cosine similarity between the points. Maybe that could also explain this variability to some extent.
Yeah, right. Yeah, it's there's certain properties when you don't want to necessarily use, for example, the cosine. Okay. How about in the context of large language models? So you have the input, which is like, let's say, lives in the token space, like, I don't know, 100,000 different types of tokens. And then like the model encodes that into the continuous like embedding space. Have you studied this, like, let's say that I have some like short prompt, I don't know, out of like 10, 15 words. Then I change individual words. And then like how does your scheme work on that? This, like, I mean, it's like basically exponential number of like different like word, like, I don't know, attacks or whatever the application is. Like, how you want to see it?
Yeah, okay. So the short answer is that we have not explored this idea. We have not tried to apply this scheme to applications such as the ones you mentioned. However, Nico, the other author, he did some work in this area. It's not. It was about. It's not about algorithmic recourse. It was more like in the context of ranking queries, where you have a prompt. You ask the question and you ask the model to produce a ranking. I think in their case they looked at medical diagnosis sort of use cases where the prompts can change slightly. You can have syntactic change in the prompts, and these changes might result in different rankings. And the way they approached the problem there was to they took a completely different approach based on computational social choice. So which I don't know if you know what it is, or in any case, doesn't matter. It's basically this branch of computer science that looks at social choice problems. And long story short, you have different rankings. You can aggregate them in such a way that you produce a stable ranking at the end. So this is one way to approach the problem.
So in the medical case, it would be that you have like, I don't know.
What are the symptoms?
You describe the symptoms, and then it's not like unstable under that you're basically adding one symptom or missing one symptom, for example, or two. And so you get still the same like robust diagnosis, or at least some like ranking of the diagnosis, the same ranking order.
Yeah. So and that is an idea that we've started exploring in this context, but it didn't work as nicely. So we tried to basically replace this step here, and actually. That also goes in the direction of your previous question on the variability that we observed. We tried to use different approximation schemes. Each approximation scheme would likely result in a different set of candidates, and then we tried to aggregate these candidates using social choice or aggregation functions from social choice, and we tried to, and we were hoping, what we were hoping to obtain was less variability effect, sets of counterfactuals that were more stable. It didn't work for the applications that we considered. To be honest, we don't know why. At the moment, we don't know why it didn't work. Maybe it's because when you have tabular data, the combination, there are many hyperparameters here. You have the diversity criterion. And then for each diversity criterion, you have different parameters that can be tuned. And in many cases, they would all collapse to the same solutions, actually. So after the aggregation, they would all collapse to the same solution. And then there are some technicalities. For instance, when we start populating the set of counterfactuals using this nearest neighbor approximation scheme, the first counterfactual would always be chosen. It would always be included in the set. Because you do nearest neighbor, you have a list of counterfactual. The first one is by definition diverse because the set is empty, so you add it. But then the problem is that this you do across all the different approximation schemes, our choice, right? This was our implementation. And ultimately what this means is that the first one will always appear, and therefore the first one will always have a higher priority in a way, which in turn kind of skews the computational, the social choice aggregation part, because you always have this guy that appears in every set. Therefore, it means that the first guy is a good candidate, but maybe it isn't. So,
could I ask you a question about your testing? You showed these different data sets and whatnot. This was robust to similar profiles, but not necessarily to inputs changing over time. Right?
No, there's no time. No.
That's a separate issue in that sense. Yeah. Okay.
That is a challenging problem. I don't actually.
So yeah.
I'm not even sure what I'm not even sure where. I wouldn't even be sure where to start. What does it mean that the input is changing over time? Is it like the same instance that is changing, and therefore you have some sort of a sequential kind of decision making?
Boundary shifts on a simple diagram, like the boundary could shift in different directions.
Yeah. But if it is the boundary, if we're talking about a shift in the boundary, then this is something that I've worked on, for instance, and this is when you have fine tuning.
Okay.
Because then the boundary changes a bit, and you can try to generate counterfactuals that are robust, where robust basically means this example is fine. Basically, simplifying a lot. This guy here would be more robust to shift the boundary than this guy here, right? And then you can find ways to kind of formalize this and be a bit more precise than what now. Yeah. But this is the idea.
It's interesting. Thanks.
And does the approach you suggest deals well with the problem that you said at the beginning, that the points are close to the boundaries, so they are not different from
right.
examples?
Right. Yes, but that is really because we are using this this nearest neighbor counterfactual explainer as a starting point. So the nearest neighbor counterfactual explainer will only return points that were already present in the training in the data set. So in that sense, I'm not expecting the data set to contain adversarial examples. So since the counterfactuals that I will return, they by construction belong to the data set, and therefore they're not adversarial examples. So in that sense, yes.
They are distinguishable from adversarial examples, or not, because they are close to the boundary?
Well, they're not necessarily. It really depends on. It really depends on whether you minimize or not. Because if you stop here, if you do not minimize, then these points they belong. These are the original instances that were present in the data set. In that case, you're guaranteed. If you minimize, you don't know what happens, right? You need to be a bit more careful. And on top of that, if you minimize, you can have other problems. For instance, as you can see here, sort of the closer you start from this set here, but then when you minimize, all the points they become less diverse, so they kind of converge, in a way. So minimization, distance minimization in that setting might also reduce, and this is something we observed. It reduces the diversity. There are challenges, yeah.
If there are no further questions, let's thank Francesco again. Thank you.